All right, welcome to part three for applications of the first derivative. This is essentially going to put together part one and two into one application, which is known as the first derivative test. And before we get into that, just to review real briefly what we've looked at, we've talked about critical numbers. That was in part two. And just as a reminder, critical numbers, these are locations where we can have a possible extreme value. So either a relative max or a relative min. And these critical numbers occur anywhere where the first derivative is equal to zero or the first derivative does not exist. So places where the first derivative may cause division by zero, or if you plug it in, you got zero over zero, etc. So any of these kind of places that don't work inside that first derivative. And so what the first derivative test is going to do is take this idea that, okay, well, if I'm at a critical number, aka where the derivative is equal to zero or does not exist, and then I take what I know about the first derivative telling me increasing and decreasing, then I can actually describe at these critical numbers if I have a max or a min. And the reason why that works, and this is going to be the kind of conclusion to the critical numbers in part two, is that when the derivative is equal to zero, this is implying that my function has ceased to change, meaning that at this moment, I either have a horizontal tangent line, or at this briefest moment, my tangent line is perfectly vertical, which is the does not exist point. And when this is happening, if I'm going from increasing to decreasing or vice versa, at that moment, then that is guaranteeing that at that moment, if I go from increase to decrease, this would create a maximum. If I go at that moment from decreasing and then I start to increase, then at that moment I know it has to be a minimum because that is the point of no change. I know that point exists. Versus if I had a vertical, essentially what's happening is if I go from increasing to decreasing and it does not exist, it's a cusp. I'm creating a corner there. In terms of that scenario. And so just to kind of help establish why the increasing, decreasing, why f prime needs to change for there to be a max or a min, take a look at the graph that I've got right here. If you'll notice, there are certain letters and certain markings drawn here in terms of x values, lowercase a, b, c, d, and e. These are all describing critical numbers for this graph. So I have critical numbers at a, b, c, d, and e. And what I want you to do is by looking at this graph, can you go through and describe at which points do I have a relative max or a relative min? And then at which point is there neither these two things? All right, and so at A, if I went here, notice I have a horizontal tangent line. That is telling me that this is a critical number. It's a place where the derivative is equal to zero. And notice because I'm going from increasing to decreasing, and this point is the highest, at A I have a relative max. I also have a relative max here at D because at this corner, the vertical, or sorry, excuse me, the tangent line here would be vertical, meaning it's going to be going straight up and down. You can kind of see how the corner lines up even with this vertical line for D. And then I'm going from increasing to decreasing, and this is the highest point on the graph. So D is also a relative max by definition. I have a relative min at B, and that would be it. So only at B. And the reason for that is notice that at B, I have a horizontal tangent line. So again, that means the derivative is equal to zero. And notice how my graph goes from decreasing and then to increasing, meaning that at this point where there is no more change, this is the absolute lowest point because I'm not going to decrease anymore. The next step is to move up. At this point, we have literally stopped, and so it establishes essentially a relative minimum, and it's the only point where that essentially occurs. I have neither at C and E, and this is really important to notice because especially at C, see how I have a horizontal tangent line at this point? So in other words, the derivative is equal to zero, but it's not a maximum because I'm increasing, but then I continue to increase. All right, so it's not the highest point when I'm concerned with the little local neighborhood here. And E doesn't work because although I'm decreasing until I get to this point right here where now the derivative does not exist, it's not a minimum because then I continue to decrease, meaning that this point right here isn't the lowest point in that neighborhood if I was to take it. the graph would continue to go down and continue to decrease. And so this is why it's really, really important that critical numbers isn't just where we stop, because this is a good example of where the derivative is equal to 0 or does not exist. But there's only really 3 out of the 5 that create a relative max or a min. And that's going to be that's where the first derivative test comes in. So the first derivative test is all about where a graph goes from increasing to decreasing, or vice versa, around these critical numbers, because then that'll tell me at these critical numbers if I have a max or a min. And so I have a description here for the first derivative test, and then we'll incorporate this. This is the procedure. So step 1 is to find the critical numbers. In other words, let's get a list of places where a max or min could occur, and then we'll use a number line, and we'll determine whether I'm increasing or decreasing. And so this is going to be very, very similar to part 1, which is why, again, these two parts kind of come to a head here. We're kind of combining part 1 and part 2 from this lesson series. And so you'll notice in A here, if f prime changes sign from positive to negative as we move across the critical number, then we say that f has a relative max. And this should make sense, because if I'm going from plus to minus here at C, that means my graph is increasing to C and then decreasing, meaning I've hit a maximum at that point. And to B, it says if f prime changes sign from negative to positive, well, that is implying that as I travel across C, I'm going down, which is negative for f prime, and then I'm going up, which is positive for f prime, and that guarantees at this exact moment where I'm 0, I'm creating a minimum. All right, now part C says if f prime does not change sign as we move across, then f does not have a relative extremum at C. That means there is neither a max nor a min. So as we saw above, although this could be a critical number right here, the graph could increase, but then continue to increase like so, and therefore this wouldn't be a max. And I could flip this for it to be a case where it wouldn't be a min. We could also see this with the vertical tangent lines from earlier. So the two things that I'm going to do, and I'll again show you in the next 3 or 4 examples, is the first step is we're going to derive and then set equal to 0. We're going to look for anything that would put a 0 in the denominator for undefined. And then what I'm going to do is I'm going to do a number line. And I'm going to check for this sign change from either going from positive to negative or negative to positive. That's what I'm looking for when it comes to the first derivative. And if you need a refresher for that, look at part 1, because we're really just looking for where am I increasing and where am I decreasing. It's the same kind of process. All right, and so speaking towards that, all of the examples that we're about to look at, and you'll notice especially in the first 2 here, example 5 and example 6, these functions we actually did in part 1. So you could actually go back and look at what we did, and it's actually the very same process. Just our conclusion won't be intervals of increase, decrease. It'll be if I have a relative max or a min. So I would encourage you to look back. I'm still going to kind of walk through at least with the process, but again, we did this process already. So if it looks familiar, that's why. All right, so example 5, find the relative maxima and the relative minima of the function f of x is equal to x squared. So if I'm looking for maxes and mins and I want to do the first derivative test, this means my very first step is to find the critical numbers, aka these critical numbers are where the derivative is equal to 0 or the derivative does not exist. So this means I need to take the derivative of x squared, so f prime is equal to 2x, and then I'm going to set this equal to 0 and solve. Divide by 2, we get that my critical number occurs at 0. So the second step is I need to know what is f prime doing around 0. So I'm going to draw a number line, and I'm going to put 0 here in the middle. I know this is all the values that I'm going to choose. I'm plugging back into the first derivative, so I'm going to put that on the side just as a reminder. And then I'm going to pick a sample point just to the left of 0, so let's say -1, a sample point just to the right, and I'm going to plug this back into the derivative because and I don't care so much the actual number, I just care about if it's positive or negative. So if I plug -1 into 2x, that'll give me -2, aka that's going to be negative, and then if I plug in 1, that'll give me positive. So see, what this is telling me is that f, the original function, is decreasing until I get to 0 and then increases. So according to the first derivative test, what do I have at this critical number? Well, we have a relative minimum at x is equal to 0. All right, because my f prime goes from negative to positive. I'm decreasing and then increasing as I move across 0, my critical number. All right, now one thing that I want to clarify here is I'm going through and I'm answering these. I am not actually finding the minimum value. I've actually just told you where the minimum is located. I know that I have a minimum, I have a minimum at x is equal to 0. So it's all about where right now. If I, if I wanted to know what would the value of this minimum was, so if I was to plot it, what would the output be? What would the y value be? I need to take this and plug it back into the original function. So I would essentially go through and say, okay, well, what is f of 0? In this case, 0 squared. And so the minimum value would be 0. And we know that because this has a vertex at the origin. It's a parabola, so I know that's going to be the lowest possible value. And so this is actually even an absolute min, if you were to really look at it. For now, though, I'm not going to be concerned too much with the actual value. I'm really just going to be focusing on where it's located, being able to describe what's happening at each critical number. All right, so let's take a look at example 6. All right, so example 6, find the relative maxima and relative minima of the function f of x is equal to x to the 2/3. All right, so again, for this one, first step for the first derivative test is to go through and find my critical numbers. So those critical numbers occur where the derivative is equal to 0 or the derivative does not exist. So I have my original function, which is x to the 2/3. I need to derive this. I'm going to use the power rule for that. So 2/3 comes to the front, x, and then I subtract 1. So this will give me negative 1/3. And remember that this negative power just means that this x exists in the denominator with that 3. And so I'm going through and I'm setting this equal to 0. And keep in mind again, and we talked about this in part 1 when we saw this problem there, that if I'm setting this equal to 0, because this is a quotient, notice how there's no x in the numerator. There's no way that this derivative will ever be equal to 0, right? There's no x value I could plug in that would zero this out because there's no x in the numerator, because that's the only way a quotient can be 0. The one thing to point out, though, is that x cannot be 0 because that would put a 0 in the denominator. Well, that establishes that this is a critical number because I'm also concerned with where I do not exist. In other words, what x values can I not plug in? I'm specifically looking for quotients like this, and I'm looking for denominators and anything that'll put a 0 in the denominator. So in this case, that would literally be 0. And so this means when I go to my number line, I do have something that I need to put on the number line. Again, that's going to be 0 as my marker. I'm going to remind myself that I'm plugging this into the derivative and that my sample points are going to be, again, -1 and +1. And you can use a calculator or just kind of talking about it in words and just kind of talking about it. If I was to plug -1 into this, this 1/3 means a cube root. It means it's going to keep the negative sign. And that means this overall is just going to be negative. You would see in a calculator, -2/3 would be your final answer. So like -0.66666. If I plug in +1, hopefully you see that this would come out to be positive, meaning that this graph is decreasing to 0 and then increasing afterwards. So this is describing a relative minimum at x is equal to 0. And if I was to go through and I wanted to know what this actual minimum value was, I would take this and plug it back into the original function. And in this case, that would be into this x to the 2/3. Well, 0 to the 2/3 is just 0. So notice the value here is actually 0 as well. Okay, so example 7. So something a little bit different that really just kind of shows you two examples where you can set it equal to 0 or have a spot where it does not exist as your critical numbers go. All right, so let's take a look at example 7. It's just a straight up polynomial. Same directions, find the relative maximum and the relative minimum of the function x to the 3rd minus 3x squared minus 24x plus 32. All right, so again, I'm going to use the first derivative test. This means I need to find my critical numbers. That's going to be my first step. Again, this occurs where the derivative is equal to 0 or the derivative does not exist. So I need to go through and derive. Well, because it's, everything's being added and subtracted, I'm just going to derive each piece individually. Power rule for each of these, the derivative would be 3x squared minus 6x minus 24. And again, I'm setting this equal to 0. We factored the 3 out to give me this here. And then we could factor, which we got 3 times x minus 4 times x plus 2, giving us my critical numbers of 4 and negative 2. Again, I kind of moving a little fast here just because we've already done this work in part 1. So if you've seen that video, then this again, you could, hopefully it's familiar. We got these same answers as before. And so the next step is to then do a number line where I'm going to now mark these critical numbers, so negative 2 and 4. And then I'm going to pick test values to plug back into the derivative. And I'm going to choose again the factored form because it'll be easier here to read off the signs. And I'm going to plug in specifically values like negative 3, 0, and 5. And again, I'm just checking for signs. And so if we plug in negative 3 into each factor pair here, this would give me a positive times a negative times a negative. So this result overall is positive. If I plug in 0, this will give me a negative. If I plug in 5, this would give me a positive. I'll leave that again as an exercise or for you to kind of go through and double check. But notice what this is describing then is I have a relative maximum now, and this is located at x is negative 2, so at that critical number, and I have a relative min at x is positive 4. And I know this because the derivative at negative 2 is going from positive to negative, meaning that my graph is increasing and then decreasing. And then when I get to 4, I'm going to stop decreasing and then begin to increase, meaning that there is again a change, and then now there's a min there. Now this again is just my locations. This does not give the actual values. So if I wanted to go through and find the actual values, I would need to take my two numbers here and plug them back into the original function and figure out what is the actual y value. And then you would see this reflected in the graph. If you were to graph the original function in your calculator or graph the original function on Desmos, we would see that the maxes and min, the max and min would occur at these specific x values, and their y value would be the overall if you were to plug it back in. All right, so let's look at example 8, and then I think I have a word problem after this. Maybe one more question. Yeah, just a word problem, then we're done. Maybe 2 more word problems. All right, so example 8. Find the relative max and relative minimum, so same directions again, for the function x plus 1 over x. Again, the goal here is to use the first derivative test. To do that, I need to find my critical numbers first. Now, when we find our critical numbers, I'm going to rewrite the original function first. And again, I talk about this in part 1 for why I'm doing this. Essentially, it's just so that when I take the derivative, it'll be easier to take. So the derivative of x is 1. The derivative of x to the negative 1. Negative 1 comes down, so it's going to make it minus. And then I subtract 1, so negative 2 there, which is essentially this, 1 minus 1 over x squared, to make that a positive power. And if I go through and I set this derivative equal to 0 so I can find my critical numbers, notice immediately I have x in the denominator, which means I do know that I do not exist here. So that is a critical number that I do not want to forget. So I'm going to go ahead and write that down. And then I'm going to go through and solve this problem like we've done before. I'm going to add the 1 over x squared to the other side, multiply x squared over, and then take the square root, giving me plus or minus 1. And so I essentially now have 3 critical numbers, 2 where the derivative exists at and zeroes it out, and then 1 where it does not. So when I go through, I'm going to do my number line now. I'm essentially finding where my function is increasing and decreasing. I have negative 1. I have 0, which is a vertical. Remember, it does not exist there, so I use dashes to denote that. And then I've got, let's say I'll be symmetric, so right here, positive 1. And again, these are breaking my number line up and essentially dividing the function up into 4 different pieces. And then I'm going to pick sample points and plug them into the first derivative. And I'm checking for their signs for the derivative. So let's say negative 2, negative 0.5, positive 0.5, and then let's say plug in 2 here. All right, and so I'm going to plug all of this in to the derivative. I'm going to use this form right here. And so I'm going to plug in -2. Well, this would give me a positive result. If I was to plug in -0.5, this would give me a negative result for 0.5, and a positive result for +2. Again, I talk more about where those signs come from in part 1, so I would encourage you to go back and look at that, or using a calculator, plug these sample points in. Overall, what this is describing then is two things. One, I have a relative max and a relative min at two of my critical numbers. Specifically, I have a relative maximum at x is equal to -1, and I have a relative minimum at x is equal to +1. And that is because at these points, my derivative goes from positive to negative, meaning there's a change there at -1. Because it's plus to minus, I know that's a max. At +1, I know again I'm going from negative to positive, so I'm decreasing and then increasing. That means I have a minimum right here at +1. Well, remember that we also had a critical number at 0 because that's where the function did not exist. Notice though that there is no change in sign around this kind of vertical asymptote here, around this point, not point, but really vertical asymptote, that the graph is decreasing and then decreasing again. So this is neither a max or a min because there's no change happening at that critical number. It's still something that we need to write out because there could potentially be a change here, but for this graph there's not. So we always have to take that into account. So my final two answers about where a relative max and min occur are at -1 and +1. And again, if I wanted to know their exact values, I could take -1 and 1 and plug them back into the original function, and that would tell me what the actual max value is and the min value is locally. All right, so let's take a look at some applied problems now so you can see kind of how this is used. What I would like to try and do is, especially in these next two examples, the focus is going to be on increasing and decreasing. These are types of problems, if you did the practice from Friday and from part 1 and part 2, you would have seen some of these word problems already. I'm gonna kind of take it to the next step here, and after we establish increasing and decreasing, I want to look and say, okay, at these critical numbers, is it a max or a min? And what does that mean? Because I'm going to try to give you some of those analysis type questions for practice. So applied example 9, profit functions. The profit function of Acrosonic Company is given by P of x is equal to -0.02x squared plus 300x minus 200,000, where that is in dollars, where x is the number of Acrosonic model F loudspeaker systems produced. Find where the function P is increasing and where it is decreasing. In other words, I want to know where is the profit going up and then where is the profit going down in terms of how I am how many speakers I am essentially producing. So in order to find increasing and decreasing, I need to find the derivative. And when I find the derivative, we're going to go ahead and find the critical numbers. So I want to know, where is P prime equal to 0, or are there any places that the derivative does not exist? Now, because we're a polynomial here, there are no places where the derivative will not exist. All right, this function is smooth and it's continuous, meaning there's no jagged edges, there's no holes, no vertical asymptotes. So I'm really only looking for where the derivative will be equal to 0. All right, and so I'm going to go through and use the power rule. So the derivative, the first term is just going to be -0.04x, and the derivative of 300x is 300. And again, I'm going to set this equal to 0 and solve. To make things easy, I'm just going to add the 0.04x to the other side and then divide by that. Dividing by 0.04, really multiplying everything by 25, and you'd see this in the calculator. You should get a final answer here as 7,500. Now this again is where a critical number is. That means that's where I either have a max or a min. Now because I want to go through and I'm going to figure out increasing and decreasing, just like when we were finding maxes and mins using the first derivative test, I'm going to use a number line and mark 7,500. And the other thing that I'm going to do here is I'm actually going to take this arrow on the left side off, because now that we're looking at a application type question, X has some limitations. In other words, when you're producing, the smallest amount that you can produce is nothing, right? This number line has an end. Now, technically, you could only produce so many items, but we'll assume that the right-hand side goes off into infinity. but the 0 does give me kind of a limit over here on the left-hand side. All right, and so just like normal, I want to go through and pick a test value, so I'm just going to choose the number 1. Why not? And then over here, I'll choose something like 8,000. I need one more 0. Here we go. To plug in on the right-hand side. Now these values again are going to be plugged into the derivative p prime, and I'm looking for positive and negative, so I'm really again only caring about signs. If you plug one in, you'll see that that should come out to be a positive answer. If you were to plug 8,000 in, you should get an answer that is negative. And so this is describing then where my profit function is increasing and decreasing. Profits are increasing from 0 items being produced up to 7,500. But then profits are decreasing if I produce any more than 7,500 all the way out to infinity. The profits will never start going back up. So then what does that tell you? How much should we actually produce then if I'm trying to maximize profits? Well, I should produce 7,500 because what the first derivative test tells me is that my profits are going to go up, but they're going to peak at 7,500. I have a maximum here at this value because the profits begin to decrease. So in other words, using the first derivative test and knowing how this function is increasing and decreasing, we can actually predict the amount for production that would actually maximize my profits. This is called optimization, and it's one of the applications we're going to look at later on after we cover the second derivative test. And it's another type of word problem, very similar to related rates. All right, so this is the maximum profits, which would be producing 7,500. All right, so a final example here, applied example 10. This deals with crime rates. The number of major crimes committed in the city of Bronxville from 2006 to 2013 is approximated by the function n of t, and you see the function listed there. The big thing that I want to highlight specifically is this part here, that t is only going in between 0 and 7. And this is going to be really important when we're solving through this question in a minute. So I just wanted to point that out. Now, n of t notes the number of crimes committed in year t, with t is equal to 0 corresponding to the beginning of 2006. So notice that t is only going until 2013, so that's why t is 7. So find where the function n is increasing and where it is decreasing. All right, and so that means if I'm looking for increase, decrease, I'm essentially using the first derivative test, which means find critical numbers. So I need to look for where is n prime equal to 0. Again, n is a polynomial, so I don't have to worry about any parts where it does not exist. So I just need to derive, so applying power rules. This would be negative 0.3 t squared plus 3.0 t, and then the plus 100. Derivative of 100 is 0, and then I'm going to set this equal to 0. All right, now what I'm going to do here, and there's a couple different ways algebraically that you could solve this, and what I do in the notes and what I'm going to do in the video is I'm actually going to factor out negative 0.3, and because both of these terms have a t in common, I'm going to factor one of those t's out, right? So it's essentially a GCF kind of problem. So out of this first term, I'm going to be left with just a t, negative, since it started out as plus and I'm factoring out a negative. Over here, I would be left with 10, and this is equal to 0. So that way, this is going to be a little bit easier to solve. Zero product property tells me to do negative 0.3 t is equal to 0, and then t minus 10 is equal to 0. Well, this tells me my critical number happens at 0, and my critical number happens at 10. Now, this is why the intervals are very, very important, because notice how this value here, my real critical number that we're going to focus on, is outside of the year range that we're looking at, right? We're stopping at 7. So that means from 0 until 10, my function is either always increasing or always decreasing, because at 0 and 10, these are the only points where it has a possible place to change. Everywhere else, it either has to be plus or minus. So when I go to my number line, I'm actually not going to stop it at 7, although that's where our interval is. I am going to actually draw it out as if we were going like normal to 10, so you could kind of see what I'm talking about. All right, I'm not going to go any further to the left of 0 because we're not looking previously before 2006. I need to pick a test value, so maybe something like 1 and then maybe something like 11. And then again, I'm plugging all of this into the derivative n prime. Specifically, I'm going to plug into the factored form right here. So if I was to plug in a positive 1, this will give me a negative times a negative, so I get a plus here. And then after 10, if I was to plug in something like 11, this will give me a negative times a positive, so this would be negative here. And so in other words, this tells me that the number of crimes committed per year is actually increasing from 2006 until 2013, all the way up really until 2016, according to this trend, or after 2016, this would decrease. But because we're only going until 2007, or excuse me, not 2007, because we're only going to t is equal to 7, we're actually not even getting to that break point there because my model doesn't support that. We're staying right here in between 0 and 7. So n is only increasing on the interval from 0 to 7. N is never decreasing. So I only have to give this single interval. According to the first derivative test, this does tell me, though, at 10, I would have a max if, again, this is the right function to model all the way past 2013. All right, so I do believe that is all the examples I have for you. So I just want to scroll and make sure. All right, and so in conclusion, what we have from this entire video for the applications of the first derivative is that the first derivative can tell me a couple things. So here's kind of the closure. All right, the first derivative can tell me where my function is increasing and decreasing. In other words, I can find these intervals. Now, in order to find these intervals, I need to find what are called critical numbers. All right, where is my derivative equal to 0 or where it does not exist? Because then my function either has to be increasing or decreasing everywhere else. Now then, the first derivative test, which I'll just call FD test here, looks at that number line and it looks at these two things and says, okay, well, if I go from negative to positive at a critical number, then this means I have a minimum at that point. If my derivative goes from positive to negative, then I would have a maximum, right? So we're able then to analyze my number line and make a read on what's happening in the original function at those critical numbers. If, right, there is no change, then that critical number is not a max or a min, which we saw in part 2 could happen. All right, and so this is everything that's really, really useful with the first derivative, which has a lot of applications when you're really thinking about it, because just even talking about min or max, you're generally trying to optimize something, right? When do I have the most money? When do I have the least amount of cost, right? When is something going to be the most expensive, right? That kind of adjective, adverb, English, again, not a very strong point, but just the idea of like, when is the optimal time for something to happen, or when is the optimal, what is the optimal decision I should make? What you're talking about mathematically is the first derivative, right? That's what you're looking at. And so that's why marginal is such an important concept from previous mod. All right, and so that's it for applications of the first derivative. We will then look at the applications of the second derivative in the next video, in the next lesson. It'll be a little bit shorter since we have all of this, so it won't be broken down into 3 parts. Make sure you look at the practice problems and you're preparing for your assessments, because this week the assessments will begin, either you writing or doing your assessments with me. Otherwise, I'll see you in the virtual classes, and if you have any questions, let me know.